So, we got all of our key steps of what to think about when facing something to do with factoring. We went to the back of our spirals for an example of warm-up. I told you to dig deep. Maybe think about Brandon's hint from yesterday, what he contributed that last example. If there's one complex zero, there must be another. They come in pairs, a good place to look in your notes. You guys have been working on it for a little bit. I'm not going to necessarily, I hit the wrong button, I hit the wrong button again. I'm not going to solve it yet. But I will give a hint. But hopefully using what you guys have already thought about. Meaning, if 1 plus, that's 1 point. If 1 plus 3i is a factor, what else is a 1 minus 3i is 1 as well. Now, there is a quick dilemma, and it might have thrown you off. Are those factors? Technically. Or are they solutions? Because, do you see x minus or x plus? That probably doesn't make much of a difference. But maybe just for a couple of you it might. They're technically solutions, not factors. Any ideas of how to start? Brandon. You could, but it would be brutal. But you could. If I just see those fourths and those thirds and those squares and binomials and what were you thinking? Plug in 3. How come?
Yeah, but then.
Okay, so he's just saying, hey, think of all the factors of 60. So 1 and 60 and 2 and 30 and 3 and 20 and 4 and that goes in, right? 15 and then 5 and ooh, that's 12 and then.
6 and 10.
Plug in the lot, 6 and 10. What?
Just took forever.
And then try them all plus or minus. You figured out this 3. But they gave us this clue for a reason. Usually if they give us 1, we can find the rest with synthetic, etc. How can we figure out what those 2 mean to the problem? Cassette, what do you think? Huh? Kind of. They are what comes out from 7 equals 0. So they already are that. How do we go to the factors? Bring them back to the x minus, I know it's weird, and x minus, somebody were like, wait, what? Isn't it x minus a? Right? Oh. Don't they come from x minus a? If these are my solutions, they came from x. Set that equal to 0 and that adds over and we get that answer. Set this equal to 0 and this adds over and we get that answer. How does that help? Couldn't we multiply and see what that is and then take it away from the rest? And when we multiply imaginary numbers, sometimes they become real. Okay, minus 1, minus 3i. What am I doing?
Not killing a seal.
Not killing a seal. Starting off. Now I say x times x. X squared. That's it somewhere. You guys keep me honest. Remember I made a mistake last time. X times negative 1. X times 3i. What? Yeah, it's true. 3i. X 3i.
Yeah.
Just because you don't like something or someone doesn't mean you're not supposed to be nice. My lesson. Keep going. Negative 1. Negative x. Negative 1 to negative 1 plus 1. Negative 1 to 3i. Negative 3i? Yep. Negative 3i to x. Negative 3i to 1. Negative 3i to 3i.
Not the most beautiful equation I've seen.
Not yet.
Oh, we're gonna cut the 3x's. That's nice.
You guys already nicely simplifying? Because it does quite nicely simplify.
Really good.
I'm missing a negative 3i and a positive 3i, which makes 9i squared. Minus 9i squared, right? Oh, hey, I can do him. Minus 9i squared, doesn't that become a plus 9? Wow, negative 9 times negative 1 is a positive 9. Huh, now what? He's gone.
No, that's minus 2x. Negative x minus x is negative 2x.
Okay, nice. So what does cancel out? He's gone. He's gone. He's gone. And he's gone. So now what do we get?
Oh, get rid of the x.
X squared minus 2x plus 10. No way. This craziness came from that? Wow. Yeah, that equal to 0 quadratic formula ends up being an imaginary number, and it came in a plus or minus of a square root in a quadratic formula. But now that we know this nice, I don't need to do undo, this nice little polynomial, x squared minus 2x minus 10, or plus 10. Now that I know that this goes into this, what can I do? Long division. Not synthetic. Synthetic means just x to the first power. There's no way we're doing synthetic with either of those. But now that it's real, oh, long division. And long division.
But you gotta keep writing the stuff that you factored, right?
Eventually, when we
Because I
write
don't
all
know
the,
what else.
when we need the zeros, yeah. But right now we're just dividing, and didn't both of these make that? And so we can say, oh sweet, this somehow goes in, this
Oh,
results in these, which results in those zeros that we already know. We just need to figure out who else is there and why. Let's say 3 didn't work. Let's say 12 did, and you didn't want to test plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 5, plus or minus 6, all the way up to plus or minus 12 to find one that works. Who wants to do that? Only 3 works. Yes. But even if we did figure out, and Luke, here's a struggle, right? And Hannah, if we know that 3 works, we could have done synthetic, but then we would have gotten a cubic, and then we would have had to go find another one. And there's no way we're finding those on our own, right? So the 3 is great, but we need to figure out something else. So what happens here? You guys are already going, right? I'm going to change colors just for sake of keeping everything even. X to the 4th minus 2x cubed plus 10x squared. Division means minus. Better be distributing those negatives. Play it safe when your points on the line. Minus x, yeah?
ooh, starts to work out pretty well.
Yep, because we know it goes in evenly. It came from their factors. Minus 6, yeah? we can say f of x is equal to, what was the original one? X squared minus 2x plus 10? That ugly one from the imaginary? Well, he's free, because 0 is reversed. Then we have x squared. You guys get x squared minus x minus 6? Ooh, yeah. We already know his ugly factors. X minus 1 plus 3i. X minus 1 minus 3i. X minus 3. X plus 2. Who are the zeros? The ones we already knew. 1 plus 3i, 1 minus 3i, positive 3, and negative. Those are you guys testing. You should have done the plus or minus.
And how did you get from plus x plus 2?
Oh, I factored. This little dude. Oh, okay. Into those.
I need nutrition after this.
You need nutrition after this? Sapping only string. That was cool. Did we find a note? What was a key? They gave us one, imaginary. Look at you guys whispering customers. We know complex zeros come in conjugate pairs, so we knew a second one. We hoped by multiplying their factors we got a real polynomial, and we did. Which is going to always be true. Then we said long division. We'll figure out who's left. Dun 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 dun. We'll factor him. Dun dun. Good.
So like if this is a test question, you need like a whole page for it.
I just used the bubble.
Yeah.
Yeah, maybe next test, 2 pieces of scratch paper. Okay, next one. Remember I said yesterday there are a few little tools at the end. We're just going to peek at them. We're not going to stress about them too much. This isn't something you have to memorize, but it is a nifty property of polynomials. Descartes, who was the same mathematician that had something to do with the Cartesian plane and Cartesian point plotting, which means the whole x-y axis idea of having horizontal and vertical components to describe something's position. Made games like battleship possible. But he wasn't thinking that back many moons ago. Descartes came up with, or his work resulted in, the rule of signs. And talks about a polynomial in descending order. And it talks about different characteristics of its zeros. And we just saw one that had a 60 at the end with so many different possible factors. This shortcut might have allowed us to narrow down what exactly we were looking for. I'll show you why in a second.
Let me see, I forgot to ask you. Why did you put, knowing that the solution could be 1 plus 3i and 1 minus 3i, why did you put x minus that in parentheses?
Because knowing that those are solutions didn't help me necessarily to know what factors they came from, hence what or how to break down the polynomial division.
Oh, you equal to 0, and then becomes 1 minus.
Kind of. You can think I had x minus a equals 1 plus 3i, x minus a equals 1 minus 3i, and I switched it so I could get my factors. And from the factors, then we could multiply, get a polynomial, we could do polynomial division. It's probably the trickiest step. given a polynomial descending order with real coefficients, the number of positive real zeros of f is either equal to the number of variations or changes in sign of f of x or less than that by an even integer. The number of negative real zeros is either equal to the number of changes in sign of f of negative x or less than that by an even integer. They must have zeros right now. Ready? No. It's okay. I'm not changing stuff. Let's take polynomials from the page before. And let's write them out. These are examples. Because we just found all of his zeros. We know what they are. If someone has that right above in the notes, I would really appreciate it. F of x is equal to x to the fourth something. I'm going to, because of what's up here, I use f of x for 1 to help me know about the number of positive real zeros. And then I use f of negative x to help me know about the number of negative real zeros. So f of x is good, but I'm going to also quickly write down f of negative x. I'm skipping a line so that you guys can see how we use this rule. Or how we could with a really nasty problem with a really big number with lots of factors. And let's say they didn't give us a clue and we just had to go for it and hope we found them. Plugging in a negative x to the fourth, that's a positive, right? Isn't that even power? Plugging in a negative x to the cubed, what happens? Negative, negative, negative? Positive times a negative? Negative times a negative 3 is a positive 3. It's going to flip the sign. Plus 6x squared, plugging in a negative x makes it positive, stays the same. Plugging in a negative x, it's going to be a minus. And then, well, minus 60, there's no plugging in, so he stays the same. Now, this obviously doesn't have symmetry. Some things changed and some things didn't. But how do we use Descartes' rule of signs? We ask. The question, what's the number of changes in signs between the terms in descending order? As you move from the fourth to the cube to the squared to the single to the constant, how many changes in sign for the first, for f of x, just normal? Well, there's 1 change in sign, right? 2 changes in sign. 3 changes in sign. One more time. Look at my cursor. Pause. Positive to negative. There's 1 change in sign. Negative to positive. There's 2 changes in sign. Stays the same. 3 changes in sign. Do you see it? As we move in descending order, there are 3 changes in sign in the first. And that's f of positive x. Oh, hey, that's a way to remember. And f of negative x. Positive zeros, negative zeros. How many changes of sign in this one? 1. Oh, literally, that's it? Okay. So what do I know about how many positive real zeros? According to my rule, it's either how many changes in sign or less than that by an even number. Oh, so 3 minus 2. Sweet. 3 minus 4, that's a negative. That can't be a how many. You can't have negative. I mean, if you're in debt, maybe. But besides that. How many positive real zeros? There was either 3 or there was 1. How many from this one? Negative real zeros. Either how many changes in sign, which is 1, or less than that by an even number. 1, or 1 minus 2 is negative 1. 1 minus 4 is negative 3. 1, no negatives.
Oh.
Because if I subtract 2, it's a negative number. I can't have the negative how many, so that doesn't work. So, for instance, if you guys were looking over here, and let's say we didn't have the 1 plus 3i, we couldn't have actually systematically for sure gotten what this was without just testing all the different possible factors of 60. And let's say that was a 2. So then we'd have to divide all of those by 1 and by 2. Almost double as many, right? Let's say, like Luke and Hannah did, they found the positive 3 to work. Sweet. If we knew the positive 3 would work, well, hold on. Shouldn't we also try negative numbers if there has to be a negative real zero? So we know this one for sure. There is only one negative real zero, so there's one negative real zero. And then either 1 or 3 positive real zeros. So we go looking for a negative 1, we go looking for a positive 1, and then we'd see what we have left. We would end up getting down to this polynomial, and then we would do quadratic formula, then we would find those two. It just kind of helps you narrow down what you're looking for. So once again, it's not something you're going to memorize. It's a nifty property of polynomials. We're not going to stress too much about it. I want you guys just to practice answering the same questions that I just did. From who is f of x, f of positive x, who is f of negative x, you're going to answer the exact same questions of what's the number of changes in sign, analyze what you have, and then we'll say how many possible positive real zeros. Might be just one option, so we know for sure. There might be a couple options. And then for negative, I'm going to ask the exact same 2 questions when you wish I had a smartboard, right? Except instead of positive, let's go negative. You don't have to actually factor in per se. It's not right now. We're just trying to answer the questions of how many possible. You guys got it? How many changes in sign of f of x? 0. Instead of you might be like, it's not an x term. That's okay. There can't be a change in sign then if he's not even there, right? So positive to positive, positive is all positive. So therefore, we have 0 changes in sign. So how many positive real zeros are there? So don't go looking at the positive numbers. That's a bad idea. You see application? If there are no changes in sign, then it can't possibly be a positive number. It's not going to work. No positive real zeros. So only look at the negative options if you were having the test. Negative. Uh-oh. Who was at the negative x? Good, because the square didn't do anything at +1. How many changes in sign? So how many negative real zeros? But a cubic has 3 zeros. There's 1 negative and there's 2 imaginary. You already know exactly what you're looking for. Wait, so if we had to factor or find the factors, let's apply this now. We would think of, right? Let's change colors. We would think of possible rational zeros, right? Remember how we do this? It was from the beginning of the section. Plus or minus what? Factors of the last number. And on bottom we have, but we already know, let's forget all of the positives and let's focus on the negatives, right? So the only ones we're going to test, -1 and -1/2. We're only going to test -1 and -1/2. Does that make sense? Let's see if that actually works. What's our polynomial? 2x cubed plus 3x squared plus 1? We just got our possible zeros. Plus or minus 1 over 1 and 2. We forgot the positives because we looked at Descartes' rule of signs. No change in sign. They must be negatives only. Those are our possible ones. Hey, we can plug in -1, yeah? Sweet. Let's just do that. So we'll test x equals -1, right? And that would end up being f of -1, which is -2 plus 3 plus 1. That's 4 minus 2. Okay. So scratch that. Let's try x equals -1/2. Assume you guys want to plug in. Maybe you don't. Synthetic with -1/2. Maybe you're like, ugh, that doesn't sound fun either. So we have 2 times -1/2 cubed plus 3 times -1/2 squared plus 1. -1/2 times -1/2 times -1/2. -1/8 times 2. We'll get back to it. Plus 3 times, what's -1/2 times -1/2? 1/4. 3 times 1/4 is 3/4. Plus 1. -2/8 plus 6/8 plus 8/8. Uh-oh. Or is that also 9? Does this polynomial have any rational factorable zeros? No. It'd be one of those nasty decimal ones you'd have to find in your calculator, and there's no other way for us to do it. Does that make sense? Although we could use intermediate value here, and we could go ahead and plug in random numbers until we see a sign change. That could be fun. But besides that, just being what I know. Besides that, we couldn't really tell much about what's going on. Although, just this. Who's that easy again? What would happen if I plugged in -2? I already know -1. Wouldn't that be 2 times -2 cubed? That's -8, yeah? Plus 3 times -2 squared is 4. Plus 1. Isn't that -16 plus 12 plus 1? -16 plus 13, -3? He's a negative number. And he's a positive number. Where's my really weird 0? I know where he is. How could I make it even better? I could plug in -1.5, and then I could narrow it down and narrow it down and narrow it down, and that could be just as good as my calculator. Anyway, we'll stop there.
Why did you equal it to 2?
Huh?
Why did you equal that to 2?
Because it's 4 minus 2 is 2. I just solved. Oh, I plugged in -2 because I saw this cube. If I plug in bigger negative numbers, this is going to beat out this one. So I knew it was going to become negative soon. Either -2 or I would have tried -3 next if -2 didn't work. Because I knew -1 was a positive number, but as I plugged in bigger negatives, this cubic is stronger than the squared. So soon I was going to get a negative, and then I could say, hey, positive to negative, IVT says if I see a change in sign, I know there has to be a 0 somewhere in that interval.
So between the -3 and 2?
-1.
Oh yeah.
X is -2, X is -1. Remember in the
Ooh,
tables,
yeah.
we would see here and we would look back here and say, oh, hey, I know where he is. And if you guys go on your calculator, it would be -1 point, I'm guessing 6. Anyone test me? Who's going to test me? I'm guessing -1.6-ish. Maybe -1 point. No.
-1.677.
Woo, look at that. All right, last tool. Yeah, last tool. We're not going to look at it. We're going to do one example and then we're done. But in the midst of all of this, kiddos, what's the big idea of section 2.5? You're given a polynomial. He's worse than a quadratic. Much worse than all of them. He's worse than a quadratic. And you're trying to factor. A couple homework problems are going to ask you to use these rules. Like one here, one there at the end. But if you understand them, maybe you could use them to your benefit. If you think about it on a test, if I was a college professor, I might just give you one horrendous polynomial and say, go figure it out. But that's not me. I do multiple choice, long answer, try to spread it out, have them worth fewer points each. Partial credit, all that jazz. Grace high school teachers can give. But these are tools that are out there that can make this process nicer. Come on there. you have a polynomial, you have real coefficients, you have a positive leading coefficient, the very, very front one. We have f of x being divided by x minus c. So, what are you doing? You're testing. You're testing what? You're testing a possible zero. You're dividing. You're either doing long division or you're doing synthetic. So if it looks like that, you're doing synthetic. This is talking about in the last row. This is talking about with the last row, the answer row of synthetic. So what this is, these are clues that you can look. You do synthetic and you're like, oh, hey, look. If c is greater than 0, if c is a positive number, and each number in the last row is either positive or 0, so you have a positive c and each number in the last row is positive or 0, then c is an upper bound. What's that mean? You're testing, let's say the ones, positive or negative, all the factors of 60. Let's say you plug in or you get up to positive 5. You're still looking for a positive one. You know there has to be one. And let's say you do synthetic and everything is positive. Stop looking. Ignore all the rest. That's an upper bound. There's not going to be anything higher. Let's say you're plugging in negative 5 and doing synthetic with negative 5. And let's say in the last row of your synthetic division, all the numbers are alternately positive and negative. Zeros are wild cards. Zeros can be either. Then C is a lower bound. If you're testing negative 5 and you have the signs alternating back and forth, zeros or wilds, they can count as either. Stop looking. None of the others are going to work. It's a lower bound. All of them must be higher than that. So when we get to this example, and it says verify the given upper and lower bounds with synthetic division. Now, they're telling you what's an upper bound, what's a lower bound. There could be many of them in the sense of if you test 5 and it's an upper bound, and if you test 10, he'd be an upper bound too. It's saying stop, don't go any further. There's nothing else out there. So we have a polynomial. If you were to plug in 4, and I know some of you are like, why are you plugging in 4? He's not a factor. If we were to plug in 4, he's not a possible factor. 2 synthetic, using the coefficients of 1, negative 4, 0, 1. And if you were to go, those hands up. Wait. There's no change in anything. Guess what? Nobody above 4 is going to work. Why? Those hands up. That's going too fast. But is there any change in sign? No. So by the theorem, is he an upper bound? Check. That's all you got to do. I'm going to go ahead and finish the other one so I can save it online. You guys get out of here and finish the rest of your brains. It's a little tedious this night and this weekend and enough to do. Homework due Monday.
How nervous are you?
Super
Hopefully it's not.
Yeah, but it's so confusing.
Bye guys.
Looking like quieter next. It stands so much. Oh, Luke. Hey, Luke. Hold on. Why are you here? Hey.
Yeah.
Where you at? Luke Ramos. Oh, sick. Good job, dude. Yeah, 38 people on 5.
According to, there we go. According to this rule, we can say by looking at a polynomial and noticing how many switches in sign. Now, does it make sense how I'm counting the switches? I get 3. What the rule says is either I have 3 positive row zeros, just stealing the number. Either I have that many, or I have that many, take away an even. So 3 minus 2. 3 minus 4, I'm subtracting 1. I have negative 1 zeros, like I have that many. Okay, if it was 10, I'd have 10 or 8. That'll help me get a problem. That's why I'm not having little numbers. Otherwise, but like this one was helpful because Because it was one takeaway, two is a takeaway. Does that make sense? But yeah, that's why we're not memorizing, but it can be helpful sometimes. Oh, this is probably like the hardest problem in here. Did it make sense if I have one complex and must have its prime? And then I said, these are just numbers. They're ugly complex numbers, A, B, I, but they're numbers. They're not factors. So then I built factors using the clue solutions, which I call A's. They can be factors when they're plugged into x minus A. So I just took x minus our ugly two numbers. So if our zeros,
Right, do you see?
imagine our zeros were 2 and 0.
And we should do after.
X minus. So I'm just taking the x minus and I'm putting him in, and the x minus and I'm putting him in. Because from solutions from A's, I make factors of x minus.
I've been seeing all my primary.
Then I said, if I multiply complex numbers, they can become real. So I did this whole polynomial multiplication of each piece having to go to every single other piece.
I'm trying to walk.
And I just did I literally did a big simplified everything. All the I stuff canceled out, and I just had a nice polynomial. He has really ugly zeros from the quadratic formula, but a nice looking polynomial. Then I said, sweet, that came out of that. Let's divide and see who else is there, which is this after dividing. Didn't do synthetic because it has a square. And then, is that cool?